Okay, in this video we're going to look at logarithmic equations. That simply means we'll be dealing with equations that have, of course, logarithms in them. And the first equation here in example 1 is 2 times this log has to be equal to 3. And if we divide both sides of this equation by 2, we'll get the log by itself. Another way of, considering this problem, if that log is equal to 3 over 2 or 1.5, we can double it and get the number 3. And of course the advantage of writing it this way is now we can go to exponential form. So this logarithm is the same thing as saying 5, the base 5, raised to this exponent, 3 over 2, must be equal to x. And we're essentially finished here, but I think we'll tidy this up a little bit and maybe even write it as a radical. And remember, if you have 5 to the 3 over 2, you can write that as 1 plus a half as a mixed fraction, essentially, up in that exponent. And by having addition in that exponent, of course, we can now write this as 5 to the power of 1 multiplied by 5 to the power of a half equals x, which means we could say x is our solution if we opted for radicals. We'll say that x is 5 to the power of 1 multiplied by 5 to the power of a half, which of course is the same thing as the square root 5. Okay, in our second example, we are now faced with a logarithmic equation where the base is unknown. So log base x of 10 has to be equal to 2. So what base is required so that when we input 10 into this logarithm, we are going to get the power of 2? Well, let's go to exponential form, and things are a lot easier to decipher. So this would be the same thing. This log is the same thing as saying base x raised to this exponent 2 would have to be equal to 10. So this is a pretty easy quadratic equation to solve. Of course, we'll take roots of both sides, and I guess at least for the time being, consider the possibility of being able to use both of these roots of the quadratic equation, x squared equals 10. Now, of course, there's an issue with one of these two answers here. Of course, one answer is saying root 10, and the second answer is, I'll write it for the time being here, negative root 10. And hopefully you can see that there's an issue with our negative answer because bases can't be negative, and we typically not only avoid negatives, but we avoid 0 and 1 as our bases as well. So even though both of these x values would satisfy this quadratic equation, we'll keep in mind we didn't start with the quadratic equation, so we have to interpret our answers, I guess, through the lens of the starting point, which of course is the logarithmic equation. So we can't state both of these answers. We only state the positive answer, and it's probably good to remind yourselves why, and that's because our base can't be negative. It can't even be 0, and it's probably also a good idea to say our base can't be equal to 1 as well. Okay, in example 3, things are getting a little more interesting. We now have a couple of logarithms, at least with the same base in this equation, so we have to figure out how to get a difference of 2 logs equal to the number 5. And you can probably guess, since the bases are the same, that allows us to use our properties of logarithms. So of course, if we have a difference of 2 logs with the same base, we can write this as log base 2, which is of course the base here. And we can write this as the division of both of those items. So x plus 3 divided by x minus 1. All that has to be equal to 5. So through condensing this logarithm, condensing it down to this quotient of x plus 3 and x minus 1, we can now, of course, have a single log equaling 5, which allows us to write this in exponential form, which would mean 2, which is our base, raised to this number 5, must be equal to x plus 3 divided by x minus 1. Now don't panic too much. That's kind of a weird looking equation there, but if we multiply both sides by x minus 1, we can clear out that rational expression on the left hand side and realize, and I guess we can also say 2 to the power 5, of course, is 32. Multiply both sides by x minus 1, and we'll clear out the denominator on the right hand side. And then we notice, okay, this isn't bad. This is just a linear equation. And keep in mind, if we get an answer, we better make sure if we look in the logs above, that we don't encounter any zeros or negatives inside our logarithms above, or then our answer would have to be rejected and there would be no solution. But let's at least figure out what our answer is here first. Of course, we'll use the distributive property on the left-hand side. Since this is multiplication across subtraction, this will be 32x minus 32, and that's equal to x plus 3. So we'll subtract x from both sides, and we'll add 32 to both sides. So we have a strange answer, but it's going to be x must be 35 divided by 31, which if you can think of as a mixed fraction, it's obviously 1 and 4 over 31. So that's basically a number a little bit bigger than 1. Now that's going to be important to keep in mind, because when we go up here and I put a number a little bit bigger than 1 here, I don't encounter any negatives. And if I put a number slightly bigger than 1 here, I don't encounter any negatives, or of course 0 in either log. So our answer is 35 divided by 31. Or of course you could opt for the mixed fraction there, or even a decimal if you wish for your final answer. Okay, in our final example here, we have the sum of two logs equaling 1. And since the base isn't written in a pre-calculus class, it's safe to assume that both of these logs are base 10 or common logarithms. So we're to deal with, instead of dealing with the sum of two logarithms, it makes a lot more sense to condense this to a single log, which I think I'll write out the hidden base 10. And if you condense a sum of two logs, of course, you'd have to multiply the two arguments or the inputs together inside your condensed logarithm. I guess using our rule of sum going backwards, instead of expanding, we are condensing here. So inside this condensed logarithm will be the product of 2x plus 1 and x minus 4, of course, the inputs and the individual logarithms above. And by doing that, just like our previous examples, we can now go to exponential form, where we have a base 10 exponential raised to this number 1 as a power, must be equal to 2x plus 1 multiplied by x minus 4. Of course, we can clean this up. That's just 10 on the left-hand side. And if we start to expand out the right, this will be 2x squared minus 8x plus 1x minus 4. And one last step, I guess it's a two-part step. We'll condense the like terms here on the right-hand side. This will be minus 7x. And as you can see, I'm getting our, I guess, cherished 0 on the left-hand side here to set up a some quadratic, I guess, possibilities. If we have a quadratic equaling 0, that will allow us to try to factor it or use, of course, the quadratic formula. So our constant will be minus 4 subtract 10, which is minus 14. So I guess we can take a look at trying to factor this. Anything going to add to give us negative 7 and multiply to give us the outside numbers of minus 28. And 14 and 2 is not even close. And I guess 7 and 4 is as close as we can get here. And that, of course, isn't going to differ by 7. So it doesn't look like it's factorable. So we'll proceed with, I guess, the quadratic formula, finish off our, I guess, or get our two solutions to the quadratic. And I guess before we do that, just keep in mind that whatever answers we do eke out here using our quadratic formula, we can only use the ones that we put into these logs and avoid negatives and 0 in both of those individual logarithms. So that's important to keep in mind probably before we go ahead and try to solve this quadratic using, I guess, the quadratic formula, since it doesn't seem to be factorable. So we would say x equals minus b, which is going to be 7. That's going to be plus or minus the square root of some stuff, we'll say, all divided by 2a, which is our x squared coefficient, of course. So in here, we would square the x coefficient, minus 7 squared. B squared is 49 minus 4 times negative 14 times 2, which of course is negative 28. So that's a bit of a mess in there. Let's clean that up and write this as 7 plus or minus the square root of a single number before we get our calcs out here. And this is all going to be over 4. So what do we have in here? We have 28 and 4, which I guess is 80 and 32. We multiply that out. Of course, feel free to use a calculator here. It's just probably easier for me to do it this way on the screencast without getting my virtual TI-84 out. And it looks like I still will probably check my arithmetic. That being said, looks like I'm going to get 161 here, 11, and yeah, 161. So let's go with the square root of 161, and we'll get our 2 decimals. Then of course we are not done until we go back and check out our logarithms and make sure we only use the x values that avoid negatives and 0 in our above logarithms. Okay, so to get the decimal approximation of the answers we got from our quadratic formula, the first one, 7 minus root 161 all over 4 is approximately negative 1.42. And the other answer is going to be 7 plus square root of 161 all over 4, and that's approximately 4.92. So to wrap up, we're going to look at the decimal approximations and see if we can, I guess, decipher which one of those, and hopefully one of them, will work in our original logarithmic equation. Okay, so here we are with our 2, well, I guess our exact answers, but probably more useful are approximations here, roughly negative 1.4 and 4.9. And hopefully we can recognize if we use the number that's almost 5, I guess if we use 4.92, we stay clear of negatives and the number 0 in that logarithm, and definitely in this logarithm. So this answer seems to check out, and that is okay. And now this negative 1.4, notice if I put it into this second logarithm, I'm going to have negative 5.42. And of course, we can't have logs of negatives. And even if it worked in that logarithm, which it doesn't, we can't use it if it fails to, I guess, avoid negatives and the number 0 in the input of this logarithm, because of course we are stuck to our set of real numbers here. So it looks like this solution does not work. And to be a little more rigorous, what you'll see a lot of people doing is they'll actually state the domain of both of these logs and make sure that the answers, I guess, correspond to both domains or stay in both domains. So maybe we'll do that quickly. The domain of this logarithm, of course, we'd have to make sure 2x plus 1 is not 0 or negative. And subtracting 1 and dividing by positive 2 would mean that our x values have to be bigger than negative 1/2. And you can see that negative 1.42 is definitely not bigger than negative 1/2. And over here in the second logarithm, the domain is x must be greater than 4. And of course, pretty easy to see that negative 1.42 is not bigger than 4 either. But notice 4.92 works in both of these domains. It's bigger than 4, and of course it's much bigger than negative 1/2. So our final answer here is x is approximately 4.92 is our approximate solution, rounded of course to 2 decimal places. And if you want the exact value, of course that's 7 plus the square root of 161, all divided by 4.